Myself, Madhuri Modak, Assistant Professor in Mathematics, Department of Computer Science, Abhiday Namdar, Senior College. Now, in groups and coding theory, we start with the last unit, that is coding theory. Now, we have seen what is the meaning of encoding function, group code, Hamming weight, Hamming distance, etc. Now, we define parity check matrix. Let m and n be non-negative integers with m less than n and r is equal to n minus m. And n by r Boolean matrix H equal to H11, H12, H1R, H21, H22, H2R, HM1, HM2, HMR, and last R by R rows form an identity matrix. Such a matrix is called as a parity check matrix. Now, Boolean matrix means a matrix whose entries are either 0 or 1. Now, first M rows contains either 0 or 1 and the last R rows form an R by R identity matrix. So, these M rows and last R rows. So, there will be total M plus R means n rows, and how many columns are there? R columns. So such type of matrix H is called as the parity check matrix. Now we use H to define an encoding function EH from Bm to Bn as follows. Now every element of Bm is an m tuple and every element of Bn is an n tuple. If B equal to B1, B2, Bm is an element of Bm, then X equal to EH of B, we define it as B1, B2, Bm, X1, X2, XR. Now the first M tuple B1, B2, Bm remain same. And additionally there is X1, X2, XR which we have to calculate by using these equations. Now R plus M. So from this R plus M is an N. So the element EHB equal to X is an n tuple. So it is an element of Bn. Now see how to calculate X1, X2, XR. So X1 is equal to B1 H11 plus B2 H21 plus and so on Bm Hm1, which is actually the row B1 B2 Bm multiplied by first column of this matrix. Similarly, X2 is equal to B1 H12 plus B2 H22 plus and so on Bm Hm2, which is nothing but row B1 B2 Bm multiplied by the second column of that matrix. Similarly, XR is equal to B1 H1R plus B2 H2R plus and so on Bm HMR, which is equal to B1 B2 Bm multiplied by the rth column. So in this way we have to calculate every element separately x1, x2, xr, and then we can write x equal to EH of B, which is B1, B2, Bm, x1, x2, xr. Now next theorem, let x is y1, y2, ym, x1, x2, xr is in Bm. Then x star h is 0 bar if and only if x equal to EH of B for some B belonging to Bm, where H is parity check matrix. Now its corollary is important. EH of Bm is equal to EH of B. B in Bm is a subgroup of Bn. That means EH, which is nothing but the encoding function obtained by using that parity check matrix, is a group code because it is a subgroup of Bn. Now the question is determine the group code EH from B2 to B5 where given parity check matrix is this matrix H. Now in this case the question is like find the group code or determine the group code, because as EH is nothing but the encoding function for parity check matrix, and by this corollary EH of B2 will be subgroup of B5 and hence it must be a group code. So the question is like determine the group code. Now to determine the group code for all elements of B2, that means for 0, 0, 0, 1, 1, 0 and 1, 1, we find all code words. Now B2 is 0, 0, 0, 1, 1, 0, 1, 1. We determine the images EH of 0, 0, EH of 0, 1, EH of 1, 0 and EH of 1, 1 by using the definition. Now by definition EH of 0, 0 will be 0, 0, x1, x2, x3 because as it is an element of B5, it is a 5 tuple. So remaining three elements x1, x2, x3 we have to find. Now x1 is this 0, 0 multiplied by the first two rows, because the last three rows is nothing but 3 by 3 identity matrix. So 0, 0 multiplied by first column 1, 0. So it will be 0 into 1 plus 0 into 0, which is 0. How to calculate x2? Again this is fixed row 0, 0 multiply by second column. So 0, 0 into second column 1, 1. So it is 0 into 1 plus 0 into 1, which is 0. Then x3 is equal to 0, 0 row multiplied by 0, 1 third column. So it is 0, 0 into 1, 0, which is again 0. So all x1, x2, x3 are 0. So finally EH of 0, 0 is equal to 0 5 times. Similar way, while finding EH of 0, 1, 0, 1 that equal to 0, 1, x1, x2, x3. Again we find x1, x2, x3 in the same way. So x1 will be 0, 1 multiplied by the first column. Then x2 will be 0, 1 multiplied by second column. x3 will be 0, 1 multiplied by third column, like that. So in this way we have to calculate all the elements. So finally we get all the code words. So required group code is set of all code words, set of all images under EH, which is 0, 0, 0, 0, 0 5 times, then 0, 1, 0, 1, 1, 1, 0, 1, 1, 0 and 1, 1, 0, 1. So this is the required group code. Now one more, let H is equal to, now this is the parity check matrix given to us. Determine the 3-6 group code EH from B3 to B6. Again by corollary, EH of B3, that is the set of all code words, is always a subgroup of B6 and hence it is a group code. So we find EH of B3, that is set of all images of elements in B3 under EH. Now if you observe this matrix H, the last three rows form an identity matrix. So we use first three rows for calculation. Now B3 contains how many elements? 2 raised to 3, that is 8 elements. So this is our set B3. Now we find all code words. So EH of 0, 0, 0 is equal to 0, 0, 0, x1, x2, x3. Again, x1 will be this row 0, 0, 0 multiplied by first column 1, 0, 1. So it is 0 into 1 plus 0 into 0 plus 0 into 1, which is 0. Same way, x2 is equal to this row 0, 0, 0 multiplied by second column 0, 1, 1. So it is 0 into 0 plus 0 into 1 plus 0 into 1, which is 0. Same way, x3 equal to 0, 0, 0 row multiplied by last column 0, 1, 1. So it is 0 into 0 plus 0 into 1 plus 0 into 1, which is 0. So EH of 000 is equal to 006 times. Similar way, while finding EH of 001, we write 001 x1, x2, x3. Now how to calculate x1? It is 001 row multiplied by first row, that is first column 101. So it will be 0 into 1 plus 0 into 0 plus 1 into 1. Now this is 0, this is 0 and this is 1. So finally it is 1. Same way x2 will be 001 multiplied by second column, that is 011. So it will be 0 into 0 plus 0 into 1 plus 1 into 1, which is equal to 1. Same way x3 equal to 001 multiplied by third column, that is 011, which is again equal to 1. So we get EH of 001 is 004 times 1. Similarly, we can find the remaining code words. Now we form the set of all code words, that is the required group code. Now see second point, decoding and error detection. Using the given encoding function e from bm to bn, we get a code that belongs to bn. This encoded word e of b equal to x is received at the receiver's terminal when transmitted through the channel. Suppose the received word is denoted by xt. If x and xt are equal, the identification of the word sent is resolved and we get b belonging to bm back. However, due to noisy channels of transmission, this is not always the case. In fact, receiving the correct code word is a very rare case in reality. In such situations, we face the problem of identifying the word B that was the original message. Now see what is decoding function, which decodes the code word. An onto function D from Bn to Bm is called an NM decoding function associated with an encoding function E from Bm to Bn. If D of xt equal to B dash is in Bm and is such that when the transmission channel has no noise, then B dash equal to B. That is, D composite is equal to identity function on Bm. Now the decoding function D must be an onto function so that every received word is decoded to give a word in Bm. See, the function is onto, it means every element in codomain must have pre-image in Bm. Now Bm contains all the words and that we have to decode it, and so the function must be onto function. The decoding function decodes properly received words correctly, but for words improperly received it may or may not be correct. Now next is maximum likelihood technique. Now this technique is used for determining a decoding function D from a given encoding function E. Given an encoding function E from Bm to Bn, we need to find an Nm decoding function D from Bn to Bm associated with E. Now see what is the algorithm to find that decoding function associated with given encoding function. Since Bm has 2 raised to m elements, there are 2 raised to m code words in Bn. Now step 1. List the code words in a fixed order. x1, x2, x3, x2 raised to m because these are 2 raised to m in number. Step 2. If the received word is xt, we compute distance delta xi xt for 1 less than or equal to I less than or equal to 2 raised to m and choose the first code word from the list, say xs, such that minimum of delta xi xt is equal to delta xs xt. That is, xs is the code word largest to closest to xt and the first in the list. Now see, the first step is first we have to arrange all the code words in a fixed order, say x1, x2, x2 raised to m. Now suppose the received word is xt. Now for xt, keeping it fixed, we find all the distances. That is, we find delta x1 xt, delta x2 xt and delta x2 raised to m xt. So we find all these distances. Then we have to select the first code word from the list, say xs, such that distance between xs and xt is minimum among all these distances. That is, xs is the code word closest to xt and first in the list. Now step 3. If xs equal to e of b, we define the maximum likelihood decoding function d associated with e by d of xt is equal to b. Note that D depends upon the particular order of code words in E of BM. That is, if the code words are listed in a different order, we obtain a different maximum likelihood decoding function D associated with E. Now, one more theorem. Suppose that E is an MN encoding function and D is a maximum likelihood decoding function associated with E. Then ED can correct k or fewer errors if and only if the minimum distance of E is at least 2k plus 1. So here this theorem gives us how many errors ED can correct and it depends on the minimum distance of that encoding function E. If it is at least 2k plus 1 then ED can correct k or fewer errors. Now, these two are important results. Let E be an MN encoding function and D be an NM decoding function associated with E. The following two statements regarding detecting and correcting errors are very useful in problem solving. First, a code ED can detect K or fewer errors if and only if the minimum distance of any two distinct code words is at least k plus 1. Means minimum distance is at least k plus 1. Second, a code ED can correct k or fewer errors if and only if the minimum distance is at least 2k plus 1. Now, one more theorem. If H is a finite subgroup of a group G, then every left coset of H in G has exactly as many elements as H. Now see example. If E is 2, 5 encoding function with minimum distance 3, then how many errors can this code detect? How many errors can it correct? Now here we will use the result just we have seen. An MN encoding function E Bm to Bn can detect k or fewer errors if and only if its minimum distance is at least k plus 1. Now here minimum distance is given as 3. So it is at least k plus 1 means 3 greater than or equal to k plus 1. It means k plus 1 less than or equal to 3. So k less than or equal to 2. Thus code E will detect 2 or fewer errors. Now E can correct k or fewer errors if and only if minimum distance is at least 2k plus 1. Now the minimum distance is given as 3. So 3 is at least 2k plus 1 means 3 greater than or equal to 2k plus 1. So solving we get 2k plus 1 less than or equal to 3. That is 2k less than or equal to 2. So k less than or equal to 1. So the code will correct 1 or fewer error. Now next example, show that 2,5 encoding function E from B2 to B5 defined by E of 00 is 5 times 0, E of 01 is 0 triple 1 0, E of 10 is 10101, E of 11 is 11011 is a group code. Consider this group code and decode the word 4 times 10 relative to maximum likelihood decoding function. Now first we have to show that E is a group code. That is we have to show that the set of code words C equal to E of B2 is a subgroup of B5. Now to show that it is a subgroup of 5, we check for identity element and closure property. Now the identity element of B5 is 0005 times, which is member of C as it is a code word. Now to check the closure property, we prepare the composition table for all elements of C. Now after preparing the table, it is observed that the operation ring sum is closed in C and C is a subgroup of B5. So we can say that E is a group code. Now we list all the code words in some specific order. Let x1 is equal to 005 times, then x2 is 01110, x3 equal to 10101 and x4 is 11011. Now we consider received word xt as given 11110. Now we calculate distance between x1 xt, then x2 xt, x3 xt and x4 xt, which we have written as delta xi xt for 1 less than or equal to I less than or equal to 4. Now what is distance between two words? It is nothing but weight of x ring sum y, that is delta xy. So to find delta x1 xt, distance between x1 xt, it is weight of x1 ring sum xt. So you can add them x1 with xt. So it is equal to 4 times 1 0. So its weight is 4 as there are 4 ones. Similarly, distance between x2 xt is equal to weight of x2 ring sum xt. So again adding them we get 1 4 times 0. So it contains only 1 1. So it is 1. So in this way, after calculating all the distances, see what is the minimum distance. So minimum distance is 1 and it is for x2. So in that algorithm, that xs is x2 here. So minimum of delta xi xt is nothing but delta x2 xt. Now what is x2? It is 0 triple 1 0. Hence we now choose the code word which is closest to xt. Here x2 is closest to xt. So maximum likelihood decoding function d of xt is equal to 0, 1 because it is given that a of 0, 1 is equal to 0, triple 1, 0. So from that, as x2 is closest to xt, from this we get d of xt equal to 0, 1 as maximum likelihood decoding function. Now third point, public key cryptography. Now the study of secret messages, its transmission, analysis, encoding, decoding process is known as cryptography or cryptology. In 1978, Rivesh, Shamir and Edelman published a research paper, A Method for Obtaining Digital Signatures and Public Key Cryptosystems. Public key cryptosystem is a method of sending coded messages using a pair of publicly known integers. This cryptosystem is known as RSA cryptosystem by taking first letter of these three persons. This method uses Fermat's little theorem as a basic result, which is stated here. Now, in RSA system, the method of encoding message or word is made public. This is known as public key, and only receiver can decode the message. That is, decoding key is secret. It is known only to the receiver. Now, this is the RSA algorithm. First step, select two primes P and Q. Second, compute M equal to PQ, N equal to P minus 1 into Q minus 1. Third, choose any integer s such that s and n are relatively prime, means their GCD is 1. Fourth, publish the integers s and m. Using s and m, encode the messages as follows. Divide the message into letter pairs alpha beta and represent each pair as a number x equal to 26 into alpha plus beta in the range 0 to 675. Replace each of these numbers x by the unique integer y between 0 and m minus 1 for which y is congruent to x raised to s mod m. Send this resulting number sequence to receiver. Now these are some results that we need while using RSA algorithm. So already we have seen the definition of congruent, that A is congruent to B modulo n if n divides A minus B, where A and B are any integers and n is a natural number. So recall, if n is natural number and A, B, C, D are in Z, then A congruent to B modulo n if and only if n divides A minus B. Secondly, A is congruent to R modulo n if R is the remainder when A is divided by n. Now, if A is congruent to B modulo n, then A plus X is congruent to B plus X modulo n. AX is congruent to BX modulo n. At the same time, A minus X is congruent to B minus X modulo n, where X is any integer. Also, if A is congruent to B modulo n and C is congruent to D modulo n, then A plus C is congruent to B plus D modulo n. Then AC is congruent to BD modulo n and A raised to K is congruent to B raised to K mod n, where K is a positive integer. Now see one example of RSA method. Use RSA method with pairs of letters and P equal to 19, Q equal to 23, S equal to 41 to encode the message word go. Now our first step, values of P and Q, which are already given to us. Now in second stage, we calculate M equal to PQ. So it is 19 into 23, that is 437. Then N is P minus 1 into Q minus 1. So again substituting, we get this answer 396. Then in third step, the value of S is 41 is given to us. Now the message is go. So it is 26 into G plus O. So it will be 26 into 6 plus 14. See how this 6 and 14 come here. So for the letters A to Z, actually we have to consider them as 0 to 25. So A, B, C, D, E, F, G. So actually G is on 7th position. But we are counting them from 0 The position of G is 6. Similarly, O is on 15th position, but as we are starting with 0, the for O it is 14. So 26 into 6 plus 14, it is 170. It is equal to X. Now we need to calculate 170 raised to 41 modulo 437. That is nothing but x raised to s mod m. It means we calculate the remainder when 170 raised to 41 is divided by 437 to get the encoded message in the form of an integer. Now 170 raised to 41 is very big number which we cannot even calculate on our calculator. So to find 170 raised to 41 when divided by 437, the remainder value we calculate it by using congruence properties. So by congruence 170 is congruent to 170 modulo 437 because 437 divides 170 minus 170. Now we do square on both sides. Now when we do square we get 170 square is congruent to 58 modulo 437. See how we get this? So we calculate 170 square which is 28900. Now divide that number by 437. Then we get some quotient and the remainder we are getting is 58 which we have written here. So this is the remainder when 170 square is divided by 437. Now we do square on both sides because we have to reach till 170 raised to 41. Now this is 170 square we got. Now next power we consider as 170 square raised to 4 congruent to 58 raised to 4 modulo 437. Now this is according to the result of congruence, that if A is congruent to B modulo n, then A raised to k is congruent to B raised to k modulo n. That means you can consider kth power on both sides. So here we have taken fourth power. So here also we have taken fourth power. That is 170 raised to 8 is congruent to 381 modulo 437. Now see how it comes. As 58 raised to 4, when we divide it by 437, we get 381 as the remainder. And by transitivity, if A is congruent to B modulo n, B is congruent to C modulo n, then we get A congruent to C modulo n. So here 58 raised to 4 is congruent to 381 modulo 437 and this already holds. So ultimately 170 raised to 8 is congruent to 381 modulo 437. Now again we do square on both sides. Then again the congruence holds. So 170 raised to 16 is congruent to 77 mod 437 in the same logic. Now one more time we do square. So 170 raised to 32 is congruent to 248 modulo 437. After taking 77 square, we divide it by 437 and find the remainder. And then by transitivity, we get this part. But actually we want 170 raised to 41. But if I do square, then I will get 170 raised to 64, which exceeds 170 raised to 41. So we use the part we have done earlier to get the power of 170 raised to 41. So I can multiply 170 raised to 32 into 170 raised to 8 into 170. So we use these equations to get the power 170 raised to 41. Now from 2 and 3, 170 raised to 8 into 170 raised to 32 is congruent to 381 into 248 modulo 437. Again, we have used one result of congruence, that A congruent to B modulo n and C congruent to D modulo n gives AC is congruent to BD modulo n. Now multiply these two numbers, divide it by 437 and find a remainder. That value is 96. So 170 raised to 32 plus 8, 40 is congruent to 96 modulo 437. But we want 170 raised to 41. So in equation 1, there is 170 raised to 1. So we multiply first and 4. So we get 170 into 170 raised to 40 is congruent to 170 into 96 modulo 437. Again do this multiplication, divide it by 437, then we get remainder as 151. So after dividing 170 raised to 41 by 437, we get 151 as the remainder. Hence, the encoded message is 151. Now these are some terminologies. Ciphers. The codes in cryptography are called ciphers. Plain text. The message to be transmitted is called plain text. Ciphertext. The message in secret form is called as ciphertext. Encryption. The process of converting plain text to ciphertext is called encryption or enciphering. Decryption. The process of determining the original message from the encrypted message is called decryption or deciphering. We consider Caesar cipher in which letters are specified for secrecy. Consider letters and their numbers as follows. So for A to M, 1 to 13 letters, we are denoting them by 0 to 12. So instead of 1, we are starting with 0. So for A to Z, the numbering will be like 0 to 25. Now what is encryption function? Fx is congruent modulo 26 rule. And decryption function, the inverse of fx. Now the first example, encrypt the letters NCP using encryption function fx equal to 7x plus 5 modulo 26. So here by using this function we have to encrypt the letters NCP. Now the letter N corresponds to the number 13. So in alphabets it is on 14th number. So as we are starting with 0, it corresponds to the number 13. So this 13 is nothing but the value of x, and for that value of x we find what is the value of fx from 0 to 25, and the corresponding letter is the required answer. Now putting x equal to 13 here, 13 into 7, 91 plus 5, 96. But what is 96 mod 26? So divide 96 by 26. So we get 18 as the remainder. So fx will be 18 between 0 to 25. Now what is the letter corresponding to the number 18? It is nothing but s. So n is encrypted as s. Similarly for next letter c. Now C is on third position. So C corresponds to the number 2 as we are starting with 0. So putting x equal to 2 in the same way we find fx. So 7 into 2 14 plus 5 19. So when you divide 19 by 26 we get 19 as the remainder. So what is the letter corresponding to the number 19? So it is T. When C is encrypted as T. Similarly, for P, it corresponds to the number 15. So putting x is 15, it is 105 plus 5, 110. So after dividing 110 by 26, the remainder is 6. So fx is 6, so corresponding letter is G. Hence P is encrypted as G. Now, one more in the same way, encrypt the message, do not pass go. Using encryption function, fx is x plus 3 modulo 26. Now, in previous question, we have to encrypt each letter separately. Now, here one message is given. So, we consider every letter in that message and then we encrypt it. The letter D corresponds to the number 3. So putting x is 3, 3 plus 3 it is 6 modulo 26. So fx will be 6. Corresponding letter is G. So D is encrypted as G. So in this way we find encryption of each letter in that message. O, N, then T, then P, A, and G. And in this way, after finding the encryption of each letter, finally we can write that message as GR, QRW, SDVV, ZR in the same order of encryption of that letter. Now, the last is decrypt the message. I am n using cipher fx is equal to x plus 3 mod 26. Now here we have to decrypt the message. So whatever is the number, it is nothing but fx, and for that we have to find the corresponding value of x. Now the first is I. The letter I corresponds to the number 8. So here fx is 8. Now we find the value of x such that 8 is equal to x plus 3 mod 26. So x is equal to 5 between 0 to 25 for which this holds. Now the corresponding letter is F. So I is decrypted as F. Now the next letter is M. M corresponds to the number 12. So again fx equal to x plus 3 mod 26, that gives us 12 equal to x plus 3 mod 26. That means 12 minus x plus 3 is divisible by 26. It means 9 minus x is divisible by 26. So x equal to 9. So m is decrypted as z. Similarly, n is decrypted as k. Hence, decrypted message is fzk. So this is the end of our unit 4, that is coding theory. Thank you.